Hello, my name is Linh. Today I will present to you my presentations about the antibiotics removal from the wastewater. Here's the table contents of my presentations. First, I will give you a short introduction. Then, about the treatment technologies include the advanced oxidation processes, biological treatment, membrane treatment, and last is the hybrid technologies. And last but not least, we will come to the conclusions. First, I will give you a short introduction about the antibiotics. Antibiotics are pharmaceuticals extensively consumed by human and animals treatment to hinder the bacteria from growing and allow human as well as animals to recover. Antibiotics consumption is steadily increasing by 30% over the last 10 years, and they have been found mostly in the effluents from the wastewater treatment plants. They are non-biodegradable, persistent, and then become accumulative in the environment. The continuous presence of antibiotics can cause the development of microorganisms resistance as the bacteria start to adapt to the increase in antibiotic levels in the environment to become antibiotic resistant. This has become an issue which can decrease the efficiency of the pharmaceuticals in health treatment. That is why it is crucial to have the proper treatment technologies to remove these pharmaceuticals from the environment. Next, I will introduce to you about the treatment technologies in removing antibiotics. First is the advanced oxidation processes. And ozonation is one of the AOPs. Ozonation is known as a widely used method in removing pharmaceuticals from wastewater treatment plant effluents. When ozone is introduced to the water, the hydroxyl radicals are generated and then the pollutants are degraded by those radicals. Those are strong and non-selective oxidant that makes the reaction of antibiotics with hydroxyl radicals consistent, contributing to the high removal rate. Depends on the types of antibiotics. The removal rate can be from 76% to 96%. And to enhance the ozone treatment, it can be combined with hydrogen peroxide, so the amount of reactive hydroxyl radicals are increased. And then the removal rate subsequently can be also increased up to 15%. In this method, it is extremely dependent on the pH level, preferably at a high pH. And it also consumes a high amount of energy, so which make the operational cost pretty high. And the second method in AOPs is Fenton process. It's the second most studied in removing antibiotics from wastewater. Fenton reaction is widely used in wastewater treatment, and its efficiency in pharmaceutical wastewater has been proved by lots of research. The removal of antibiotics is achieved by the formation of strong hydroxyl radical that leads to oxidation of pollutants and also the nature of coagulations of both ferrous and ferric ions. The Fenton method can be enhanced by the combination with other methods such as the UV Fenton or called photo-Fenton process. With this combination, the removal rate can be increased up to 90%. Several factors are included to have an optimal photo-Fenton process, such as the initial antibiotic concentration, the contact time, the reagents ratio, but pH is the most sensitive one, and the optimal pH level is 3. Moves to the next treatment method, we have biological treatment, which includes aerobic methods, anaerobic methods, and the combination of both. In aerobic methods, the process has a supply of oxygen, so microorganisms can grow and break down the pollutants into carbon dioxide and water. The sequencing batch reactor is a prime example of aerobic system. With this method, 86 to 95% of antibiotics can be removed. This method depends on the properties of antibiotics, so is quite selective and not suitable for the wastewater having many types of antibiotics. With anaerobic methods, the anaerobic microorganisms are used to degrade compounds into biogas without the presence of oxygen. Anaerobic digestion and anaerobic membrane bioreactor are the most two popular systems of this method, and the efficiency of these systems can be from 60 to 90%. If the anaerobic digestion is highly affected by the temperature and the antibiotics residues, so the anaerobic membrane bioreactor is prone to fouling, which significantly affects the removal rate of the systems. Due to the possibly unstable conditions of anaerobic treatment, the removal rate cannot be so high. So that leads to the idea of combining both methods. Membrane bioreactor with both methods, anaerobic and aerobic, it's found that no antibiotics residues are found. And they also have found that the removal of antibiotics occur under aerobic or anaerobic conditions. So it's probably the combination of both is better than a single treatment. As I mentioned before, the biological process have been proved to be potential solutions to remove antibiotics from wastewater. However, the selective antibiotics for treatment is maybe the biggest drawback of this biological treatment, which makes it not so cost effective. With the membrane method, the pollutants are separated and changed into a concentrated phase. The figure here shows the removal rate of different antibiotics by different membrane technologies, including reverse osmosis and nanofiltration. In general, the efficiencies are high. Particularly with reverse osmosis and nanofiltration, the results can be more than 90%. The rejection efficiency for uncharged organic compound depends on the size of pollutant molecule and the pore size of the membrane. For the charged compound, the charge and interaction between the solute and the membrane will affect the rejection process, and fouling is an issue of this treatment. At last is the hybrid technologies. For each treatment, it has its own pros and cons. So hybrid treatment is developed to minimize the risk and maximize the removal of pollutants. For example, in some AOP treatments, the antibiotics residues are still present in the environment, causing the potential risk to the human. So it is studied that AOPs can be combined with the membrane treatment. So it works as the pre-treatment to improve the degradation level, then followed by the membrane to remove the pollutants. With the combination of phantom and reverse osmosis, the removal rate can be up to 99%. Or with the combination of biological method with metfentan, more than 97 antibiotics are removed, such as macrolides, sulfonamides, and sulfonamides. So, to sum up, antibiotics can be removed by various methods, such as ozonation, phentan and phosphophentan, aerobic methods, anaerobic methods, reverse osmosis, nanofiltration, or the combination of those techniques. Each process has its pros and cons, but to kind of minimize the risk or the drawbacks, as well as maximize the performance of antibiotic removal, hybrid technologies seems to be the most promising solution for the removal of antibiotics from wastewater. However, because the characteristics of wastewater will differ greatly in reality, so depending on those properties, a suitable method will be chosen. And here's my main references for the research. Thank you for listening.